Okay, so here we have our block being pulled by some force with an applied force of 40 newtons, and our block has a weight of 50 newtons, and the angle that is created is 30 degrees as it's being pulled across the rough surface. And we know that our coefficient for static friction is 0.6 newtons. Well, it's just 0.6. And our coefficient for kinetic friction is 0.4. This is based on our specific type of rough surface, because depending on what surface it is, these numbers will be different. So the first thing we have to do is draw our force diagram. We're going to have our normal force going up and our weight going down with 50 newtons, that's given. And we know that our normal force is going to be smaller than our weight because the box is being pulled by a force that's pulling slightly upward and to the right, and for some reason it's just going to decrease the normal force. And we also have friction moving in the opposite direction of our motion. So now we should draw our vector sum diagram. So we have our applied force, and then we have our weight going down, and friction, and normal force going up. We're assuming that our acceleration is going to be 0, by the way. That's why we don't see a net force vector, because it should the sum of all forces should add to 0 if we're having our acceleration equal to 0, which means our object is not moving. Okay, so first things first, we have to find our friction, and we just use this equation, the coefficient of our friction times our normal force. And we know it's 0.6 for the coefficient, but we don't know our normal force, so we have to find that out. So basically we just we want to find this piece here. And the way we do that, so we just use our trigonometry skills. We know this side, we know this whole entire side is our weight, but we want this little piece here. And we're just going to subtract the normal force minus this piece, the weight, and we'll get weight minus normal force for this little area, this length. So we just use sine of 30 degrees over the opposite side times over the hypotenuse, and we'll get weight minus normal force over our applied force. And then we rearrange it so we get normal force by itself, and we plug in the numbers that were given to us already, and we end up with normal force as 30 newtons. Okay, so now we're going to try and find our friction based on what we calculated for normal force, assuming that the acceleration is 0. And so we get the coefficient of static friction times normal force. Now I know our normal force. And we get 18 newtons. This is what, based on our surface, that's what it can provide, the friction that it can provide, assuming that our acceleration is 0. And we also get our kinetic friction, but that's not important yet. And just to check, we should try and get the friction over here, not basing it on anything. Okay, sorry. So now we're going to actually calculate the friction required for our acceleration to be 0, and we use our trigonometry using cosine rule of adjacent over hypotenuse, and we get cosine of 30 degrees equals our friction, because this part right here is the same length as our friction, so we just use that, like move it up, over our applied force here. And we end up with 34.6 newtons, which is the force needed to overcome our block's motion and make our acceleration 0. that does not sound right, because if you look at our static friction, that's what our surface can provide, assuming that our acceleration is 0. 34.6 newtons is bigger than our assumed static friction. So that means that our box is actually accelerating, because friction is not enough to overcome our block's motion using what we calculated here. Okay, so now we have to redraw our entire force diagram, vector sum diagram, because now I know that there's actually acceleration. So the only change we're going to see is at the bottom here. This vector length over here, the friction is going to be shorter compared to this vector sum diagram, and now we're going to have net force, saying that there's acceleration. And we have to calculate our net force. And we can do that by using trigonometry again. Just move these vectors up, and we use our triangle. Cosine of 30 degrees equals our adjacent over hypotenuse. Our adjacent is now net force plus friction over our applied force. And we isolate our net force, and we plug some numbers in that we already knew. But hey, I have to mention this. We're going to use 12 newtons as our friction, because now that we know our object is moving, we're going to use our kinetic friction provided by our surface, not our static, since our object is now moving. And that'll give us 22.6 newtons for our net force. And now we can calculate our acceleration, and we know that net force is equal to mass times acceleration. So now we just plug in some numbers on this 5 kilograms. I already calculated the mass in the beginning when I didn't really know what to do. So I just did weight equals our strength of the gravity field times our mass, which is unknown, and then put in the weight, 50 newtons, and isolated it to get 5 kilograms for our mass for the box. When we go back down, plug in some numbers, and our acceleration is equal to 4.52 meters over second squared. Now that we have our acceleration, we can go back to what Mr. Day wanted us to find out, which is our final velocity at time t equals 10 seconds. Okay, so we don't know our final velocity, but we know our initial velocity, 0 meters per second. So now that we have our acceleration, we can draw our acceleration graph, and we can get our change in velocity, which is just the area under the acceleration graph. And we get 45.2 meters per second. And from that, we can calculate our final velocity at time 10 seconds. Our initial velocity plus change in velocity is equal to our final velocity. And we know our initial velocity is 0 meters per second plus our change, 45.2 meters per second. And we get 45.2 meters per second for our final velocity. Thank you for watching.